We'll get going this morning. Welcome everybody. Hope you had an enjoyable evening to wild and wonderful West Virginia. I was saying to people that Stellafane has Breezy Hill. We have Squall Hill.
Yeah, no kidding.
We outdo them this weekend.
Microburst Mountain.
Microburst Mountain.
Something.
Our first speaker this morning, we have two speakers, is Bill Burton, who's a member of the club. He's also one of the volunteers at the Turner Farm Observatory Park, Analemma Society, and Fairfax County Parks Authority. And he's going to talk about his program with citizens and instruction and using observation of the moon as an instructional tool in astronomy. So Bill, welcome.
Thank you, Alan. Well, great to be back here. It's been about 7 years for us. And I was actually at the first AHSP in 2005, and I gave a talk there. But we didn't have all this fancy equipment. I used one of these, and I'm not advancing. So, yeah. I used one of these. Anyone know what these are? Okay. Transparencies on this. I gave a talk on light pollution, and we had one of these in this room. So times have changed a little bit. So here's an aerial shot of our new observatory. This is stolen from Pete's talk without his permission, but he's giving a thorough talk on what our activities there this afternoon at 1:30, and I just borrowed this slide. But you can see the shed, you can see the roll-off, and he'll give details on that later. But this is where we're holding our classes now, and we're getting better at designing classes that are bringing the public in. And I'm going to be talking about one on the moon. And here's the interior of this. Again, I'm going to let Pete do most of the detail on that. But you see 3 permanently mounted go-to scopes. And then in the fourth corner, there's an imposter, which is my aging 8-inch f7 Newtonian, which I convinced them to put in there on its 30-year-old German equatorial mount. It's mostly a lunar and planetary scope. It gives very good images. In fact, I'd say it gives that AP over in the other corner a run for its money, but I'm naturally biased. So what we do with this program, so this is a class called Exploring the Moon. It's a 3-part class. I like to have people move around to different activities. So we actually start outdoors. And what I have, and I always have the kids do this, so what we do is we walk through the orbital motions of the Earth, Sun, Moon system. And I have them kind of figure out the seasons, the phases of the moon, and all that. So here we have a young gentleman holding the sun. The sun is a G-class star, so we have a green ball for that. It's actually just a medicine ball I picked up. And the girl over here has the Earth, and it's a spinnable Earth. So I just took one of those spinning globes and took the base off. And what's important, so I'm going to have her walk a circle around him, but I point out in the sky where Polaris is, so she has to keep the axis of the Earth pointed towards Polaris as she walks around the sun. And this is a little bit tricky for a kid to figure out. And I always have to remind them, no, you got to get your axis back. And then she's got to spin the ball while, she walks around. So you get the idea. So then we go, well, we're in the northern hemisphere. Where should she go to make it summer in the northern hemisphere? Winter, and then we do, the equinoxes on either side, and everyone else is kind of getting this. The idea is to kind of get you off the planet and looking down as a 3D view of the solar system. And I've done this program for years. I used to do it at Novak star parties, and it really works. So, and then you can add a third component. Oh, this guy here, he's unfortunately blind. He's carrying a silver soccer ball. That's the moon. So you got to get the moon in the system. So she's walking around the sun. I kind of freeze them for a bit. We go through the phases of the moon. How do you see them? It's all perspective from Earth. And, the sun's got to be here. So what position do we put the moon in to get a full moon visible on Earth and a new moon? you know, and then the first and last quarter. So they go, again, they see all that geometry in 3D, and walking around, it's a great, great activity for them. And then in the grand finale, we recreate all the motions. So she's walking around the sun, and he's got to run circles around her as she's walking around the sun. Now, one thing we left out is what direction do you go in? And that's not inherently obvious. This is where astrology comes in, the signs of the zodiac. So years ago, I had these beautifully painted signs made. And if you get them lined up in the right order, you see you have the dates on there. And then if you know some constellations in the sky, like just any two, or any two signs of the zodiac in order. So I have the people line up so that the zodiac, I mean, they're not right in the sky, but they're kind of correctly sequenced relative to each other. Then you explain, well, if it's your sign, if you're in Virgo now, that means the sun appears to be in Virgo, which means the Earth has to be on the other side of the sun, so you can position Earth correctly. Well, if you go from Virgo to Libra next, that means in order to get that perspective, the Earth has to be going this way. So you work out that, you know, using this method, everyone discovers that you go in a counterclockwise. The Earth orbits in a counterclockwise direction around the sun. And this is the best way I know how to demonstrate that, you know, to figure it out. And then similarly with the moon, if you go through the phases and the timing of day and all that, you figure out the moon is going counterclockwise around the Earth. So we work all that out, and that can take a good half hour. Then we go into the classroom. Oh, well, here's some geometries here. You know, when I looked at, I didn't really kind of realize the moon is actually more upright with respect to the ecliptic than the Earth, duh. Because there are areas of the moon that never see sun, and you certainly can't say that about the Earth. So here's just some geometry of that, and I can show that slide to them. And then we go into the classroom, and I have a PowerPoint that can take, 20 minutes. So here I introduce them to lunar features. What are we likely to see on the moon? What do they mean? What story, what geologic story are they telling us? And we kind of go through how you figure out what formed on the moon first and then what came later. And we call this the geological principles of superposition and cross-cutting relationships, and I'll demonstrate that. So I do that in a PowerPoint. I also have some geologic maps of the moon laid out. I have some lunar orbiter prints, and I have lunar samples. Well, the lunar samples you want to show are basalt, and I have a hunk of lava from Hawaii that's good representative basalt. And the other one, and that's black, the other one is anorthosite, which is kind of an unusual rock on the Earth. It's all feldspar. It's white. But those two, I mean, they're black and white. They can't be more contrasty. So I have those lunar samples, and I pass them around, and I say, look, the entire lunar surface is made up of these two materials, plus brecciated mixtures of the two. So the lunar surface is getting pounded and pounded, sort of like a mortar and pestle. So you have these two rock types, and then the broken up mixtures of those two rock types covering the entire surface of the moon. And then part 3, we go out to the observatory itself, and we use two of the telescopes. The AP refractor, we put, Pete has a high contrast, a low light video camera, so we attach that to the refractor, and that goes to a video screen, a laptop monitor, which is over near the other telescope, my 8-inch Newtonian, and that's what they're going to do their observing in. So after, and what I'm going to talk, I'm actually going to give you the slideshow. I'm giving you the overview, and then we're going to go into the slideshow I give them. But they've already seen the slideshow, and they're familiar with the types of lunar features. So here, I've got a live video feed of the moon, and then I'm pointing out to this woman, you're going to go look for this feature in the telescope. Because there's no other way to do that. I mean, you've got to show them an image. You can't say, look down to the lower right, because you're looking at some really tiny features. And when they look in there, all they see are craters, thousands of craters. So it's very difficult to point out exactly what feature you want them to see. So Pete and I hit upon this idea. So, I'll say, here's the crater Posidonius down here. I want you to look for that in the eyepiece. And, and that works. They can see the tiniest little features that you point out to them thanks to this method. And here's just a screenshot of, we got Mare Crisium here. We got the Raid Crater, Proclus, and, a bunch of other things. Serenitatis over there, or Tranquillitatis, I guess, Mare. And again, I can point out small details on the screen. They can go see it and go, I get it. And then I'm going to just kind of run through the slideshow that I give them. And this is kind of the theme. We start out, which came first? So reconstructing the geologic history of the lunar surface using these geologic principles. So the most basic thing, what's the most basic fact of the moon when you look at it? What do you see? What are the, there's two main things you see, right? Light areas and dark areas. So we have, so this is what I show them, and we have Maria and highlands. All right, so which came first? Well, one basic thing you need to, of course, realize about the moon is that it's constantly bombarded, right? You got asteroid-sized objects down to micrometeorite, and it's been, ever since its formation, it's been subjected to this steady rain of material. So using that knowledge, you can kind of intuit which of these is older, the Mare here or the highlands. Well, obviously, the most heavily cratered thing, it's been around more, it's been exposed longer. That must be the older surface. And this came along after many of these craters had already formed and it's less cratered. And we use that principle all over the solar system. Presentation last night, she talked about how they judge resurfacing by craters, and we've done it on the moon, on Mars. So the amount of cratering is an effective kind of relative dating tool. This is an obvious one. Which came first, the Mare or the craters? Well, obviously the craters, impacted, and they came after the Mare. And at this point, I've explained these Maria are flood plains of flood basalt. So very much like Hawaii, you had thin sheets of lava coming out, covering the surface layer after layer, very fluid, and not only compositionally, but the low gravity helps the lava spread out, and it really made a smooth surface. But this one's a little trickier, isn't it? We have, which came first, the crater or the Mare? Here's Mare lava, Mare lava, Mare lava. So which one came first here? The crater or the Mare? The crater. The crater impacted because, it was originally much deeper. Then the Mare filled in. So in this case, those relationships are reversed.
So Bill, we can also see, interesting on this photograph, that there's really no obvious way that the Mare that are outside the crater flowed into it, which means that the interior of the crater, actually, the Mare that come out from inside the crater.
Right. Yes, very good. And then we also have craters that fill up with lava without any Mare around them. And my favorite is, I'm blanking out on the name, but it's filled to the brim with lava. And there's no obvious way that the lava could have come in from the side. And what's the name? It's right on the limb, and I know it well. Yeah, that one. So there are many ways we can have lava-filled craters, and what Myron's saying is correct. Here's another one. Same thing. The crater preceded the Mare. We're at the edge of the Embryo Basin, a big impact that filled in with Mare. And an added twist here, you see that the rim here is actually submerged in the lava after. So you had the crater impact, you had the major Embryo impact, and then this crater actually tilted down in towards the basin, and that rim got inundated and it flooded in that way. So that probably was a case of direct inundation of that crater bowl by lava. but it also shows the tremendous kind of warping effect that the giant Embryo impact had. Here's another obvious one, Hercules Crater, which came first? Well, the big one or the little one, and obviously the big one came first. But this all kind of looks trivial, but when the geologists were reconstructing the geologic history of the moon, they actually used these relationships. We had no other way to tell relative ages, so it was like detective work. They were looking through telescopes. So they would look at, cratering rate, on the surface. They'd look at things like ejecta blankets, which one overlapped another one, and they carefully parsed out, what were the sequence of events that formed the features on the moon. Here's another one, a little subtler. So we have Theophilus, Cyrillus, and Catarina craters. Of these two, which one came first, the upper right one or the lower left one? The lower left, right? You can see that's a little older, it's more degraded, and then this one came in. So that's not too bad. It would be harder, however, to tell which one of these came first. Again, you'd have to look at subtle things like maybe secondary craters from this one got into this one, or vice versa, or their ejecta blankets, one overlapped the other, and so on. So again, that's what they're, in the 60s when they were preparing geologic maps for the Apollo mission, this is the kind of thing they did, is they tried to slowly piece together the history, geologic history of the lunar surface. Well, here's an obvious lake crater, Tycho, right? Rays splattering out, covering just about everything else on the moon. And this crater may be less than 100 million years old, which is very, very recent. I'll go into that in a minute for lunar history. And due to steady bombardment of the solar wind, materials that are first exposed on the lunar surface steadily darken with time. So when you have a fresh impact, the rays that come out, spray out, are always bright. And then they slowly darken with time. And that's another way to relatively date things. So Tycho has bright rays, whereas Copernicus does not. Those rays have gone away. So we know, for instance, that Tycho is younger than the crater Copernicus. And then just types of craters. This is the simple type. It's just a bowl. Less than 20 kilometers diameter. They tend to look like these bowls. This particular crater was famous. It's in Mare Serenitatis. This Russian astronomer in the late 1800s declared that it had disappeared, and people couldn't see it. The crater went away, and there was a big, hoopla, and then they discovered that, it was a bad night for him or something, and it was rediscovered by other astronomers that had never gone away. So that's a simple crater, and then you get up to a certain size and you get complex craters, greater than 20 kilometer diameter. And complex craters, well, they have a bunch of features. This one's unusually complex, Copernicus, but the main thing is they have what they call a central peak. So when you get to this size, the impact comes in, and then there's a crustal rebound in the middle. And that actually comes back up, and if the crater later fills with lava or ejecta melt, those peaks are usually emerged in the middle of the crater. And so and these are all over the moon. And you have to get to a certain size to get that central peak. We have examples of this on the Earth. One of the most famous is called Goss's Bluff in Australia. And those mountains in the middle, they go up many, many kilometers. That's not for me. The other things about Copernicus, then you have this kind of unusual scalloped rim. Well, that's due to the rim actually collapsed. These are actually landslides, giant landslides. So after the crater formed, it excavated out, there was a rebound, but the sides all slumped in. And that's a common feature of these. And then you had, I think that's ejecta melt in the middle. I don't know if there's any lava in there or not. Then you had there's actually a little volcanism associated with this. And then on the outside, this funny striated stuff here is the ejecta blanket. So this is melted rock and breccia coming out, covering the surrounding areas. And you had particles coming, you had rocks flying out, and they form what we call secondary crater chains. So you see all these here. And they tend to form, they have to be like one diameter away. So, 100 kilometers, you go out 100 kilometers, and that's about how far the trajectory of these things. And then they come back to Earth, come back to the lunar surface and make these chains of secondary craters. Yes?
You said volcanism? I came in late. Could you explain what that is?
Well, I'll go in. So lava coming out on the lunar surface, and I'm going to go into that next. So there are volcanic features on the moon. Yes.
What sort of a time interval does this take place in? Like, the crater comes down, bang, the ejector comes up, starts to fall back down.
Yeah.
And the sloping starts to take place. How long a period of time is that?
I got to ask Gene Shoemaker that very question. He gave that talk once, and that was my question. And it takes, it's like a few minutes for that whole morphology to form, the central uplift and the ejecta going on. Just a few minutes for that completely to form. And maybe even the ejecta. Now, the lava can come in actually millions of years later. There can be a delayed response to that. But most of this formation takes place in a matter of minutes. And it's a good question. And then above, beyond complex craters, we get impact basins, and some of these are multi-ringed. So you can actually have multi-ringed craters, and there's one of those exposed in the Canadian Shield, where you see the satellite image, it's a lake, and then there's kind of a ring, and then there's another one inside that. And this is probably the best known example, Mare Orientale. It's only visible on the limb of the moon during favorable librations, favorable looks at that side of the moon, because the moon does kind of vary a little bit, with respect to us. So this obviously this shot wasn't taken from Earth, it was taken from the Lunar Reconnaissance Orbiter, which is still going around and taking images. But you can, so the outer, the outer part of the impact was here, and then you had a rebound. Instead of a central peak, you had a central ring. And then it filled in with lava after that.
What size is that?
Sorry, I have it on there. It was 900 and some kilometers across. And that's not too big. Imbrium is that size. Most of the big impacts are, in the 1,000-kilometer range.
Have the central mountain in the middle?
No, because it has a central ring. So let me see if I can go up again. Backspace. Does that work? Yes. So instead of a single central uplift, and I guess I didn't make this very clear, I think it's these mountains are an uplift ring. Okay? So again, you have to be above about 300 kilometers diameter to get a ring uplift instead of a peak uplift. Someone else can probably answer this. Any guesses? Tens of kilometers for sure, I forget what the ratio is. It 10 to 1 for impacts? I don't remember. So we'll have to ruminate on that. This is much smaller. Yeah, I'm going to say 10 to 1, something like that. Yeah. This is another kind it's a kind of an offshoot where lava filled in, the crater formed, lava filled in, and then there was kind of additional, what we call intrusion. So more lava came up and kind of cracked the lava that had already solidified. And there's a bunch of these on the moon, too, that you can see. And they all have these funny-looking floors. They got cracks going. The floors are flat, like they were filled with lava after impact. Then you got these funny cracks running through them. And they're just lumped into a class called floor-fractured craters. And I bring them up because some of them are very prominent. This one is very, a good one, first quarter moon object. So you might as well know what it is. So and now I'll go into, other kind of classic geologic features. This is the most famous fault on the moon, the straight wall. Again, a good first quarter, 6-7 day old moon object. And it's just a straight line. So I tell people to look for, just this thin black line, And that's something you can actually point out without the help of a video or another screen. It's usually conspicuous enough. And you can see it's only 400 meters high. And of course, the sun angle has to be very favorable. If you look at this, the sun's coming from the right here, so the scarp must be facing left because this is in shadow. But hey, it's only 400 meters high. And you can see detail on the moon in a small scope that's down to, 100 meters or less, a few tens of meters if you get the light just right.
I didn't know about its existence, and I discovered it like 2 months ago, just by sheer accident. I looked up and was like,
Isn't that great to discover it on your own? Isn't that wonderful? Oh, so what's going on here? So this is the kind of the Earth, the analog to it. So we call this a normal fault. And I have that term in there. So this block, went down relative to this block. So this side went down relative to this side. Yes?
What's just to the left? There's sort of a curvy line. Is that related?
Okay. So this is a rill. And I'll go into rills in a minute. Any really thin, sinuous feature, it doesn't even have to be sinuous, any thin, snaky feature on the moon is a rill. But there are really two types of rills, and I'll go into that in a second. But that's the kind of thing you want to look for when you're looking through your telescope and ask, what the heck is that? So here's another type of fault, and in this case we have two normal faults facing each other, and you make a faulted valley called a graben. And here we can use the principle of superposition. Which came first, this cratered terrain or the graben? Well, you can see the graben cuts across everything, and there are no big craters in it. So this whole surface formed, and then this graben, this fault valley, cut right across that. These are usually in response to giant impact basins. So I forget where it is here, but there's one either over to the right or the left. And the stresses in the crust kind of make these radiating faults, and then they kind of operate along. There's subsidence along the fault. So again, here's the model, because these are common on Earth, so we're very familiar with them. And this is a graben on Earth. So you have two normal faults facing each other, down dropping in the middle. And it's perfect explanation for what's going on here. So this again is a rill. But we'll see other kinds. And this is the most well-known one, the Alpine Valley. And it's cutting the Alps. And the Embryo Basin, major impact is over here. And the Embryo Basin produced radiating lines all over. In fact, it's kind of structurally the most influential large feature on the moon. There's a lot of things, a lot of kind of these linear features, and you can see that they all point back to Embryo, and they cover a large part of the near surface of the moon. And two of these kind of came together and formed this fault valley, which cuts straight across this mountain range and clearly formed after those mountains were present. So that's the Alpine Valley, and it's probably the easiest one to see in a telescope. Okay, other geologic features, if you look at lunar mare under low light, you typically see these kind of funny features that are called wrinkle ridges. And these are formed as a result when this lava flowed out to fill the impact basin. It cooled and contracted. And when it contracted, it kind of shrinks and you get kind of a space problem. And the lava compensates. And we actually discussed this last night for some of the other planets. The lava compensates for kind of shoving up one side against the other. And these, on Earth, these would be called thrust faults. And I'll show you the diagram. So again, here's a cross-section of these wrinkle ridges. So in here, it's the opposite of a normal fault. So the upsloping side, you have so the arrows here are reversed, and you have one rock thrust over another. So you get this kind of space accommodation, and this would be the wrinkle ridge that's shown on the surface. And so if you went on the moon, you would see a thrust fault right along here where this kind of went over that way. And in some cases, they reverse polarity, and you've got the leading thrust fault over on this side. But again, the mare basalt's kind of trying to accommodate itself in a smaller space, and it does so by forming these wrinkle ridges. Okay, the other type of rill. There are two types. One are those fault valleys I showed you. The other type are really snaky things that go along the surface. They're always in mare. They're always associated with some kind of lava deposit. And these are considered lava channels. So near the end of all that deposition, that outpouring of basalt, you had some late ones come along the surface. And in some cases, they're buried. They're actually lava tubes. And then the roof can collapse to expose the channel itself. But we have analogs to this on Earth. There's one on Hawaii, the big island of Hawaii. There's Kilauea in the distance, and the lava's coming out and just kind of snaking along the surface. It's an exact analog to what was going on the moon over 3 billion years ago. Here's Apollo. I talked to one person, a colleague of mine at the USGS. This was her favorite mission. I think the setting and the samples they got were the most interesting. And they came right up against the rill. So they landed, I guess I have a shot. They landed right here and went down to the edge of the rill, and then they kind of went over here in their rover as well. So here they are on the edge of the Hadley Rail. You know, and while we're here, you can see the surface has all just been pulverized. You know, that's called regolith. But down to a certain depth, I forget, a meter or two, it's just powder. And it's because of untold billions of micrometeors. It's pounding the surface, subduing the landscape. It kind of does the equivalent role of rain on the Earth, all right? It just subdues everything. One famous lunar geologist he insisted that the lunar landers were going to disappear into this stuff. They knew that stuff was there. He insisted that this isn't going to work. Those landers are going to come down and they're just going to disappear into a deep cloud of this and never be seen again. Fortunately, he was wrong.
But they put really big feet on the lander.
Just in case, yeah. Here's another volcanic feature. Again, this is a good first quarter moon thing. This looks like, some of the other things, it looks like a lava channel. It even kind of looks like a a graben. Here's actually a graben here for comparison. This is a fault graben. But this thing's snaking along, and they looked at it, and if you look closely, you see a bunch of roundish craters in here. But these aren't impact origin. These are actually volcanic vents. So lava was coming out of these things. So they're volcanic craters. This one here, which I think is Hyginus A, is actually called the largest volcanic crater on the moon. And that's easily seen in a small telescope if you know where to look. So let's go to the analogy on Earth, go back to Hawaii. Fissure eruptions. And when Hawaii starts a major volcanic event, commonly you have these new fissures opening up and fire fountains of lava come out. I've never seen that. Maybe, hopefully in our lifetime they'll come back. But you can see that this fissure has just opened up. Lava is pouring out. These fountains can get up hundreds of feet high. But that's the Hyginus rill being formed there. Volcanic domes. Well, you've probably all heard of the Mount St. Helens Dome. Here's one called the Valentine Dome, again around first quarter, low light illumination. This is right on the edge of where Serenitatis kind of bleeds into Mare Imbrium. And it's a very subtle feature, very broad. Really looks more like a shield volcano on Earth. Very, very low relief. You can see it's got a graben, a rill cutting across it afterwards. But they consider it a volcanic dome. And analogy on Earth, this is a volcano in Chile, and here's the lava dome here. On Earth, the lava tends to be a little stiffer, and the domes are a little higher than on the moon, but low gravity, basalt, so that probably all contributed. Other kinds of eruption, volcanic ash eruptions. This is a good one to see. We saw this picture of Hercules. This is in the northeast quadrant. I see the moon. I look at the moon upside down, okay? I'm in a reflector. So for me, it's on the lower left, but if you're in another scope, it might be the upper right, or if you're in a mirror reversed, it might be the upper left. But anyways, these two craters are a prominent pair. We talked about Hercules earlier with its crater. But this is Atlas. It's a floor fractured crater. You can see rills crossing and stuff. And this is a good thing to see in the full moon. You'll see two dark patches in there. These are, and in the middle, if you look carefully, you see little holes. Those are volcanic vents. Black ash came out of there. And this is kind of a hard thing to see on the moon. So volcanic ash deposits, there are a couple other places where they're as well displayed. And this is an easy one. It actually shows better in your telescope because in full moon, this area tends to be bright white, and these still show up as dark patches. So see if you can see that next time you look at the moon. In this class, I go over Apollo missions sort of briefly. You know, here's one we got, you know, the lander and the rover, and I had one kid say, "Why is that thing waving in the wind? I thought there was no atmosphere on the moon." I said, "Well, you know, publicity. They put a little wire in there, and they make it look like, you know, it's waving or something." And the positions of the lunar landings. We talked about Hadley Rail, which is right in here. That's kind of one of the more challenging ones to look at. Apollo 11 at the edge of Tranquillitatis is not, I can show them where it is, but there's nothing there that's really distinctive. Whereas seeing the Hadley Rail in this narrow valley, that's a good challenge to see in a telescope. And then you can see, you know, some of the others in there.
17 is also a really interesting site visually.
Which one?
17, the Taurus Love Road.
Oh, yeah, Taurus, yeah.
See in some of their photographs, there's a landslide that occurred off North Massive. You have to see that in good seeing at high power.
So that would be over here, right?
Yeah, that's it.
I'll take a look at that. Thank you, Myron. I'm still discovering stuff. I only started this a year ago or less. I think, I'm a geologist. How come I don't know more about the moon than I do? It's so well illuminated, it's easier to show geologic examples on the moon than it is Earth, you know. For heaven's sakes, I should know this stuff better. So again, here's the Apollo 15 landing next to the Hadley Rail. Okay, so obviously one of the main things, they not only saw stuff up close, they brought back samples. Here's a white and black rock. Remember, we talked about that. So here's anorthosite, the white rock. This actually isn't basalt, it's breccia, but it might be of basaltic composition. And then a thin section of this, so you take a rock, you slab it so light can go through. And, you know, it's pulverized. It's pulverized from more impacts after it formed and so on. And the vast majority of samples they brought back were in that condition, so they kind of had to, you know, put the jigsaw pieces back together and figure out what's going on. But they knew there was basalt in the Maria, but they didn't really know what the highlands are made of, and they were a little surprised it was all this funny feldspar rock called anorthosite. That was an original discovery. And then here's basalt that was brought back. This looks pretty normal to us, and you can pick up pieces of that in Hawaii. Or if you want a nice, go over to the Shenandoah Park, you can find ancient versions of that rock. So I talked earlier about kind of doing the detective work and how the sequence of events came together. So before any samples were brought back, the lunar geologists on Earth pieced together this whole timeline. And geologists there's no geology hike here, but you learn about stratigraphy, which is the sequence of layers that formed as the Earth is formed, and you do so. And this is lunar stratigraphy. So you start out, the oldest is down here, kind of hypothetical early crustal rocks, and then volcanic. This is all conjectural because none of these materials have survived to the present in their original form. But geologists like to assign ages to this. So this was the pre-Nectarian age. And then we went up to the Nectarian age. Well, Nectarian, it's a kind of a hypothetical basin. I think it's still kind of visible, but it's been so obliterated by subsequent events. It's kind of an early giant impact. Produced basin and crater materials, volcanic materials, maybe. They don't really know much. And then you get into stuff that we can kind of see. So the Imbrian series was created during the Imbrium impact that produced Mare Imbrium. So we have crater materials. And now they're not talking about the mare lavas that came out. They're talking about the ejecta that came out from that giant impact and spread over the rest of the moon. And then maybe some volcanic materials, but then we start to, so you have these giant basins, and then the last one, the last big basin, they consider to be Oriental. That was that multi-ring thing we saw on the limb of the moon. And then you kind of get into the more recent era that produced features that we can see, you know, with our telescopes and we're more familiar. And this is when the mare flood basalts poured out onto the moon. Now notice there are no times attached to this yet. This is all, relatively speaking, this was worked out before we had any dates of any rocks. So the main mare forming period is in here, and then some of the older craters, and then the younger craters. Eratosthenes is a crater that not too far from Copernicus and looks very much like it. But they've decided that's a little bit older, so they named this period after them. And then kind of the pretty recent, relatively speaking, Copernicus period, dominated, as typified by the Copernicus crater. Tycho being the last major crater during this period. So the flood basalts had kind of tailed off by this point, and all you had left was continuing minor impacts, producing these craters, with Tycho being the last major crater on the moon. Now, when we brought back the lunar materials, we could use isotopic dating. The most common one was the decay of potassium and argon, and that can give you age of these rocks in millions of years. Now, this diagram's a little complicated, but down at the bottom you have ages. In eons, that's a fancy way of saying billions of years. So 4.55 billion. That's considered to be the original when the moon was formed. Around 4 billion years ago, you start to get kind of a solidification of the moon and materials surviving, and they've got, basin deposits and breccia stuff. But again, there's nothing we can recognize today until we get really into the Imbrium period. And then the flood basalts come out. And now we have actual dates. So from 3.2 billion to 3.8 billion, most of the flood basalts poured out on the moon. How much of the moon did they cover? Well, that's where you look at this graph. It looks like they covered, according to this, about 15% of the moon. Well, you go, wow, it looks like more than that when you look at it. But there's the far side of the moon that we can't even see from Earth. If you look at that, there's hardly any mare basalts on the moon. So most of them are facing our direction.
So you're talking about area there?
Yes, area, percentage of lunar surface area. So 15% of the moon during this period, 3.2, was covered by mare basalts. And then after 3.2 to about 1 billion years ago, we had more basalt come out, but it actually covered a smaller area, about 5%. So we had this big outpouring, and then a minor outpouring kind of finished everything off, and then it was over by whatever this is, 1.2 billion. Yes?
Was it mostly tidal forces that caused the...
Yeah, so let's discuss, and you might have a better answer than me. Well, we'll discuss that in a minute, the near side, far side thing. But anyways, bringing back samples and dating them was, the next big key to the puzzle about how old all this stuff was. And we were a little shocked at how old everything was. Yes?
That was my question. I think a moment ago you said that the moon was considered to form about 4.55 billion years ago.
Yeah.
The Earth was, as I remember, was formed about 4.5.
Same time, yeah. Maybe a little later. Well, I'll go into that at the end here. We'll cover formation next. So we just discussed this brief. Near side, far side. Why the difference? Well, I'm not even sure what the current theory is. I think maybe this part was originally facing outward and that way got more impacts. But clearly the near side that we see had more major impacts, more lava pouring out, more mare flood basalts. And basalt is way more dense than anorthosite, the highland material. So this side, in terms of gravity, this has a gravity anomaly. It's much heavier in gravity than the far side, which is almost all Hyla material. So that side eventually got pulled towards Earth gravitationally and then locked, gravitationally locked. So that's all we see. Well, one of my wishes has always been, I wish the moon, if I had one wish, can I have the moon rotate, please? But at least we got stuck with, I think, the most interesting side. Because if we had been seeing, this is really just about all cratering. There's a few piddly little mare. But we did at least get the interesting side to look at if we're only going to get one side. So that's a blessing. And then since Apollo, we've had orbiter missions and so on. Here's Clementine, went around, did a detailed topographic mapping of the surface, did some element mapping, so we knew some areas were rich in some elements and some others. This is the topography. This basin was this is the South Pole Aitken Basin. We didn't know about this existence of this basin really until I think even after Apollo. This is actually the deepest area of the lunar surface. And it's a possible target for further explanation because there might be ice down in some craters that are permanently shadowed on the moon. So we've had orbiters ever since. There's been dozens of missions to the moon total. The Lunar Reconnaissance Orbiter. The Lunar Reconnaissance Orbiter is picking up new impacts. So here's a before and after. See the new crater? It's right there. And they estimate, they say the average is about every 23 days, a new 10-meter or larger crater forms on the moon, every 23 days. Well, 20 years ago was the first time amateurs actually saw impacts, right? Was it the Leonid, wasn't it? We didn't even think we could see them, and then, amateurs got so clever they realized they could actually image impacts. So they're going on, that rain of material continues still. And of course, the Earth, getting even more than the moon. We just can't, most of them burn up. That's Pete's bailiwick. All right, lunar formation. This is still the most popular theory for it. Mars-sized object, crashes into Earth. This explains several things. A tiny core of the moon, a large mantle, the kind of screwy, high inclination orbit of the Earth. It tends to explain a lot of things. Here we are a little while later. There's the Earth, the disk of material that came out for the impact. The moon is slowly growing. It's sweeping up that material that was in a ring around the Earth. This is like a 2-week-old article, so that's the latest vision of what's going on here. And then, who's old enough to remember Life magazine, this issue? This was actually the year I was born, but my parents kept all those issues, the world we live in. And when as a 5-year-old or 6-year-old, I started reading them. That may have been what first turned me on to earth science. And I said, I got to be a scientist. This is too cool. This picture is by Chesley Bonestell, one of the famous space artists. And what's interesting is that it's probably accurate, still accurate in some ways. So when the Earth, if you go back to this image, here's the Earth. The whole surface in this depiction is molten. So we hypothesize that the whole Earth's surface was molten. And on the moon, I'll cover this more in a minute, the light scum floats to the surface. That's the anorthosite. Well, maybe the same thing on the Earth. So the Earth may have been similar to the moon in the beginning, where it had an anorthositic crust that floated to the top, and then that's been obliterated by subsequent plate tectonics. But maybe it was very lunar-like at the very beginning. So here's that scum floating. We have a magma ocean, they call it, covering the entire Earth, and then the scum is starting to solidify, and then these things kind of slowly come together, and lo and behold, you get your first continents forming. And then after that, the plate tectonic system sets up, probably with the aid of water. You need cooling of this, you need pressure differential, then slowly you get basalt forming, and it's dense and sinks in, and you get the whole kind of conveyor belt system that we have today which in my opinion was the reason we have life on Earth. There was no way you could evolve higher forms of life without that constant change and churning. So here's Earth, protoplanets. Now, probably the biggest criticism of this image is the appearance of the moon. What do you think might be wrong with this image? I told you about the ages. So let's say this is 4 billion years ago, okay? What's wrong with this picture of the moon? Too many mare, right? It looks too familiar. So Bonestell took kind of a modern thing. Hey, he changed it a little bit, but here's the Embryo Basin, and maybe that was still there, and Serenitas, Tranquil. It looks too familiar, okay? It wouldn't have looked quite that familiar. That was the only thing he might have gotten wrong, okay? The moon wasn't quite that evolved yet. Here's the crater Plato. Well, that wasn't around yet, so.
He's got it close to the Earth, though, which it was.
Yeah, oh, that's right. Good point. So it was close to the Earth and then slowly migrated away. So still a wonderful picture. And again, I was saying this explains some interesting features on the moon. Tiny core, very thick mantle, pretty thin crust. And so when you have major impacts, this is Oriental, it wasn't hard for fractures formed from this impact to penetrate down into the mantle, which is right here. This is from a USGS paper. And then that lava leaks up through cracks and then starts pouring out on the surfaces. Lava flows filling these impact basins. But again, that didn't necessarily occur right away. They think it took millions of years. There was a big lag in some of these. There's, hundreds of millions of years in some cases between the actual impact and the eventual filling with lava.
So all this heat and lava came from the impact?
Yes, and internal. The lava, no, actually, that's wrong because of that lag. If it had come up immediately, you would have said, oh yeah, it was the heat from the impact melted the rock and so on. But what happened was the impact formed fractures that penetrated the mantle, and then this is much warmer to begin with. And so that lava kind of came up slowly. And that's how we have volcanic features, volcanic processes on Earth. Lava magma slowly makes its way up from the mantle.
The impact that formed the moon in the first place.
Pardon? Oh, yeah, this is after the moon is formed.
So that must have generated a tremendous amount of heat and melting.
Oh yeah. Well, that it was completely molten to begin with, and then things solidified out. So, it took some millions of years for this all to settle out. Maybe between 4.5 and 4, for all this to settle out. The dense elements, go to the core. Intermediate density goes here, and the crust is that anorthosite scum. The basalt mare, that basalt's a little denser, so it came from the upper mantle, wasn't originally on the crust surface. And then these impacts form, conduits down where they could feed that dense basalt, and being hot, it's buoyant and can actually make it to the surface, even if it's a denser rock, yeah.
Melting associated with crater formation lasts, like I said, minutes or maybe hours for cooling.
Yeah.
For cooling. So that's a much quicker event. But the other thing, while you have Orientale, I did a quick check. They estimated about 40 miles the impact diameter.
Okay, thank you.
Miles, which gives you about a 15 to 1 ratio.
Yeah.
I think it's about 10.
Good, yeah, thank you very much, good. This is really the last slide, and so at the end of this, I have a shot of what we're going to see that night. So I've only done one of these so far. It was a 6-day-old moon. My next one's August 2nd. We have a 9-day-old moon, and so this is what they're going to see, and assuming it's clear. And then these are some of the the major features we want to see. And I just have one coda. This is kind of a love note to AHSP. I was here 7 years ago when Rod Molise was here, and I had a mirror, this is just an aside, that I needed something to do, and he said, get an Astrosystems telekit. They're great, So I went out, next year I got one, and it took me years, but I finally made my own big Dobsonian telescope. And I bring this up because here's the scope, here's our big camping tent, and they all fit into that Prius back there. So if anyone's interested in getting one of those things, you can talk to me. I've been through it. So thank you very much. Hour and a half? Sorry. I took way longer than I thought, but you're a great audience. Thank you.
You said you were gonna go short.
Yeah, I know.
I have a question about the group you teach. How big has it been, and
Well,
how many classes?
Yeah, so again, I've just started. We have set the limit at 15, because that's about as many as we can fit in the observatory reasonably and get everyone to see stuff. And I want them to have a quality experience. Limit of 15, ages 9 and up. And, we originally started designing class, let's do adults, and so on. Doesn't work. I mean, it can work, but if you really want to fill your classes, you got to get down to kids level. We decided, we asked the advice of an experienced county teacher, programmer. What do you recommend? She said 9 and up. That gets fills their language SOPs or whatever they call it for grade school, and ticks off a bunch of boxes. So that seems to work. Both my classes have full enrollment, and again, I'll let Pete talk about the observatory this afternoon. Any other questions? Okay, thank you.